Good morning, everyone. Today, I am going to explain about the low-pass RC circuit for ramp input signal. Whenever you can apply a ramp input signal to the low-pass RC circuit, what is the response produced by the low-pass RC circuit? So here, the figure A represents the ramp input signal, and figure B represents the low-pass RC circuit, and figure C represents the response of low pass RC circuit for ramp input signal. So it is from this waveform it is clearly observed that at a t equal to 0 the input signal is equal to 0, and for t greater than 0 the ramp signal increases linearly and its value is 0 for t less than 0, and its value is 0 for t less than 0. Now the operation of the circuit is divided into two cases. That is, first case when the input signal is equal to 0, second case at t equal to 0, second case for t greater than 0. That means when the input signal increases linear motion. Now, in the first case, at t is equal to 0, the input signal is also equal to 0. Whenever we can apply that 0 signal to the input of low pass RC circuit, initially we can assume that there is no voltage across the capacitor. Therefore, for the 0 input signal, the response produced by the capacitor is also equal to 0. So initially there is no voltage, that means the output voltage is 0 at t is equal to 0. That is clearly represented here. So at t is equal to 0, the input signal Vi is equal to 0, C is not responded, and the output voltage V0 is equal to 0. In the second case, for t greater than 0, the input signal increases linearly. The input signal increases linearly. So whenever the input signal increases linearly, that linearly increasing signal is applied to the input of the low pass RC circuit. At that time, the capacitor goes into charging condition. Therefore, the voltage developed across the capacitor is in exponential motion. Therefore, the output voltage follows the voltage across the capacitor. Hence, the output voltage is in the form of the exponential motion. So that is clearly explained in case 2 operation. At t is equal to 0, the output is equal to 0. For t greater than 0, the output voltage increases exponentially. Therefore, we already know the general expression for low pass RC circuit, that is equation number 1, that is Vi, that is equal to RC into dV0 by dt plus V0. That is represented with equation number 1. Similarly, we also know the expression for ramp input signal. That ramp input signal is defined as Vi of t, that is equal to alpha t for t greater than or is equal to 0, and it is 0 for t less than 0. That means for t greater than or is equal to 0, the input signal is alpha t. For t less than 0, input signal is 0. That is represented with equation number 2. Equation number 1 and equation number 2. Now substitute the value of Vi into equation number 1. Substitute the value of equation number 2 into equation number 1, that is alpha t, that is equal to RC into dV0 by dt plus V0. Alpha t, that is equal to RC into dV0 by dt plus V0. Now, after substitution, apply Laplace transform to this equation. Here alpha is the constant value. Therefore, Laplace transform of constant signal, Laplace transform of t is nothing but 1 by s square. Therefore, alpha by s square, that is equal to, here RC is the constant value. So therefore, RC is constant value. Therefore, same RC is written as Laplace transform of dV0 by dt, that is equal to s into V0 of s. Similarly, Laplace transform of V0, that is equal to V0 of s. Laplace transform of V0, that is equal to V0 of s. Now, after applying the Laplace transform to this equation, we can get this one, that is alpha by r square that is equal to RC into S into V naught of S plus V naught of S. So here V naught of S is common, therefore take V naught of S as common. Now the remaining equation can be written as SRC plus 1. Therefore alpha by S square, that is equal to V naught of S into take RC also common. So when RC also taken as common, therefore S plus 1 by RC. Therefore V naught of S, that is equal to alpha by RC whole by S square into S plus 1 by RC. V naught of S, that is equal to alpha by RC whole by S square into S plus 1 by RC, that is equation number 3. Now apply partial fractions to the equation number 3. Therefore we get V naught of S, that is equal to A by S plus this equation, A by S plus B by S square plus C by S plus 1 by RC, that is equation number 4. V naught of S, that is equal to A by S plus B by S square plus C by S plus 1 by RC, that is equation number 4. Now take LCM to this equation. So therefore alpha by RC, when LCM is taken for this one, therefore V naught of S is this one, alpha by RC whole by S square into S plus 1 by RC. Therefore numerator is remains. Therefore alpha by RC, that is equal to A into S plus 1 by RC plus B into S plus 1 by RC plus C into S square. A into S plus 1 by RC plus B into S plus 1 by RC plus C into S square, that is represented with equation number 5. Now when S is equal to 0, apply two conditions for S is equal to 0 and S is equal to minus 1 by RC. Calculate the values of A, B, C. To get the value of B, substitute S is equal to 0 in equation number 5. So therefore alpha by RC, that is equal to, when S is equal to 0, first term is 0. When S is equal to 0, third term is also equal to 0. Therefore alpha by RC, that is equal to, S is 0, that means B by RC. Therefore RC cancel. Therefore alpha is equal to B. That means B is equal to alpha. Similarly, substitute S is equal to minus 1 by RC in equation number 5. When S is equal to minus 1 by RC, the term A term is 0 and B term is also equal to 0. Only C term is appeared. Therefore alpha by RC, that is equal to S square, that means minus 1 by RC whole square into C. Therefore RC, 1 RC, 1 RC cancel. Therefore C is equal to, cross multiply this, therefore C into is equal to alpha into RC. So this is equation number 7. It represents the value of C. It represents the value of C. Consider equation number 5 and expand. That means substitute, consider this equation number 5 and expand. Therefore alpha by RC, that is equal to, multiply this value with inside A into S square plus AS by RC plus BS plus B by RC plus CS square. AS square plus AS by RC plus BS plus B by RC plus C into S square. Now equate the S square terms to 0. So there are two S square terms. One is AS square, second one is CS square in right side. There is no S square term in left side. Therefore A plus C is equal to 0. Therefore A is equal to minus C. We already know the value of C, that is alpha C. Therefore A is equal to minus alpha into RC. That is equation number 8. Therefore we obtain the values of A, B, C. The value of A is minus alpha RC. The value of B is alpha. The value of C is alpha RC. Now substitute these three values into partial fractions equation. Therefore V naught is equal to A by S, that is minus alpha RC by S, plus B by S square, that is alpha by S square, plus C by S plus 1 by RC, that is alpha RC. Now apply inverse Laplace transform to this equation. apply inverse Laplace transform to this equation. Therefore, we get V naught of S inverse Laplace transform is V naught of t, that is equal to minus alpha RC into 1 by S inverse Laplace transform is 1. Therefore, plus alpha into 1 by S square inverse Laplace transform is t. Similarly, alpha RC into 1 by S plus 1 by RC inverse Laplace transform is e power minus t by RC. Now, in three terms on right hand side 3 terms have the value of alpha. Therefore, take alpha as common. Therefore, minus RC plus t plus RC into e power minus t by RC. Now, therefore, V naught of t, that is equal to alpha into t minus RC into 1 minus e power minus t by RC. So, this is the expression for output response of low pass RC circuit for ramp input signal. For ramp input signal, that is specified in equation number 9. Now, apply two conditions. If the value of RC is far greater than t, what is the expression for output voltage? If the value of RC is far less than t, what is the expression for output voltage? Now we are going to do this one. Now apply the condition, that is RC, the time constant value is far greater than the time period of the input signal. Therefore, the value of e power minus t by RC is approximately equal to 0. Therefore, V naught of t, that is equal to alpha into t minus RC. V naught of t, that is equal to alpha into t minus RC. That is the expression, equation number 10. If RC is far less than t, then expand e power minus t by RC. Then V naught of t is equal to alpha into t minus RC into expand this e power minus t by RC. Therefore, 1 minus of 1 minus t by RC plus t by RC whole square into 1 by 2 minus t by RC whole cube into 1 by 6 and so on. Now in this, take this minus term 2 inside. Therefore, minus 1 plus 1 cancel, minus into minus plus t by RC minus t by RC whole square into 1 by 2 plus t by RC whole cube into 1 by 6 and so on. Therefore, alpha into t minus, take this RC inside, RC cancel. Therefore, minus t, minus into minus plus RC 1 RC cancel. Therefore, t square by 2 RC minus t cube by 6 R square C square and so on. Neglect all the higher order terms. Plus t minus t cancel here. Similarly, neglect all the higher order terms. Therefore, we get V naught of t, that is equal to alpha into t square by 2 RC. This is the expression for output response V naught of t for RC far less than t. For RC far greater than t, the output response is V naught of t, that is equal to alpha into t minus RC. And this is the expression for output response, generalized expression for output response. Now coming to calculate the transmission error, we already know that what is the meaning of transmission error means. It represents the deviation between the input and output. The deviation between the input and output is represented by a parameter. That parameter is called as transmission error. That transmission error is defined as Vi minus V naught by Vi. Therefore, that is equal to, we know the value of Vi, that is alpha t minus alpha into t minus RC, because we know the value of V naught here, alpha into t minus RC by alpha t. Therefore, alpha t cancel, alpha RC by alpha t, alpha cancel, therefore RC by t. Therefore, transmission error is equal to RC by t. This is the basic general expression. Now, up to the specific time period, up to the particular time period at a t is equal to t, the transmission error is given as RC by t. So, this is the final expression for transmission error. Now this equation represents that the transmission error is inversely proportional to the time period of the input signal, and it is directly proportional to the resistor and capacitor values used in the circuit. That means if you clearly observe this graph, if the value of RC is far less than T, the transmission error is also less. If the value of RC is far greater than T, the transmission error is more. So according to this equation, this graph is represented here. So this is the response of low pass RC circuit for ramp input signal. Initially, we discussed about the basic operation of low pass RC circuit for ramp input signal. Next, we derived the expression for output response without any generalized output expression. Then we applied two conditions. One is RC far greater than T. One is RC far less than T. Now, two equations are obtained. One is this, other one is this. Next, we calculated transmission error, that is ET is equal to RC by T. This is the transmission error. So, thank you so much for your patient listening.